So as I had mentioned in the last lecture, we're going to be going over compact sets. And compact sets are really important when we're talking about continuity, which we'll be seeing in chapter 4. And before we even define what a compact set is, we're going to have to define what an open cover is. So by an open cover of a set E in a metric space X, we mean a collection of open subsets of X such that E is contained in the union of those open sets. So for example, maybe you've already seen this example if you've taken analysis on the real line. If we had the open cover 1 over n and 1, this is an interval, right? And this interval with infinitely many subsets of the real line, which is 1 over n. So for example, an open subset would be 1 over 2, 1, that interval, but then also 1/3, 1, and 4th one, so on and so forth, right? It seems like we're approaching 0, 1, right? So for example, if we were to have the interval on the real line 0, that should be over here, 0, 1. Well then, this open cover up here, these open sets cover is an open cover of E, which is the interval 0, 1. Why? Because all these subsets, if we just keep going on and on, we're going to be that although the union of all those open subsets do cover the whole open interval 0, 1. But now what is a compact set? Now that we know what an open cover is, what is a compact set? Well, a subset K of a metric space X is said to be compact if every open cover of K contains a finite subcover. And that word there is really important, a finite one. More explicitly, the requirement is that if G sub alpha is an open cover of K, then there are finitely many indices alpha 1 through alpha n, such that K is contained in the union of all those open subsets with indices alpha 1 to alpha n. So what does that mean? Is 0, 1 a compact set? We know it has an open cover, right? It has infinitely many open covers. But this open cover specifically up here, can you choose finitely many of subsets of this form or intervals of this form, 1 over n to 1, such that it covers 0, 1? The answer is no. You can't choose any, right? I can choose 1 over a huge number, let's say 10 to the 10 to the 10th to the 10th, 1. That's 1, and then also, I don't know, just choosing random ones. So on and so forth, but I only choose finitely many. Now, this here you can say is closer to 0 than 1 over 72 or 1 over 4, but it still won't. There will still be numbers close to 0 that are not in any of the finitely many intervals. Right? You would require infinitely many subsets of this form over here to be able to cover the open interval 0, 1. Therefore, the open interval 0, 1 is not compact because we can't cover it with finitely many open sets. So the interval 0, 1 does not have a finite subcover. Therefore, it is not compact. Visualization of this compact is if our set E here was what looks like an orange or brown. Here the blue is the open cover G sub alpha. And we're only choosing finitely many So over here in blue, we just choose G sub alpha sub 1 union G sub alpha sub n, because there's only finitely many. That still covers E, right? It still covers the Brown thing, the Brown set E. That's what it means for something to be compact. Okay, so with that said, we observed earlier in the last lecture that if E is a subset of Y and Y is a subset of X, then E may be open relative to Y without being open relative to X, meaning E is open in Y, but E isn't necessarily open, or it's not open in X. That's what we mean by E is open relative to Y. So the property of being open thus depends on the space in which E is embedded. Compactness, though, as you can read here, behaves better. And we're going to have a theorem. But before we do introduce that theorem, we need this lemma. And I excluded the proof. You can find this proof in the book, The Principles of Analysis by Walter Rudin. And this lemma says, suppose Y is a subset of X. A subset E of Y is open relative to Y if and only if E is equal to the intersection of Y and G for some open subset G of X. So if you like, take a second to kind of digest that, see what that means. And again, if you want the proof, you can find it in the book. But we're going to need this lemma to show this next theorem. And this theorem says, suppose K is a subset of Y, Y is a subset of X, then K is compact relative to X if and only if K is compact relative to Y. So this is a biconditional proof. And it isn't too hard to follow, but if you like, you can pause it and make sure you understand what the theorem is even asking, right? If you're going to attack or try to prove this theorem, we need to know what it's even saying. So we go on to prove it. First direction. We're going to suppose K is compact relative to X. And before I read anymore, we're going to show that K is also compact relative to Y. So again, as the proof says, suppose K is compact relative to X, and let V sub alpha be a collection of sets open relative to Y, such that K is contained in all those sets, right? Because K is compact. So we're choosing these V sub alpha to be open relative to Y that cover K. Okay, by the lemma, we're just using this lemma just now. By the lemma to the left, there are sets G sub alpha open relative to X, such that V sub alpha is equal to Y, the intersection of Y, and these open sets G sub alpha that are open in X for all alpha. And again, maybe you, if you want, you can pause this video to kind of see how it relates to the lemma. Here we're using V sub alpha, so whatever alpha you choose, V sub alpha is equal to that intersection Y of the intersection between Y and that G sub alpha corresponding to whatever alpha you chose. And this is true for all alpha. Well, that means that since K is compact relative to X, we have that K is contained in some finite subcover, right? That's why we have from 1 to n, because it's finite, for some choice of finitely many indices alpha 1 through alpha n. So again, K is contained in some finite subcover of X. Well, now we just relate that line with the previous one. Since K is in Y, well, we also have that K is contained in finitely many V sub alphas, right? From V sub alpha sub 1 to V sub alpha sub n. And because of this equation, this lemma was really important. That's what I'm underlining. That guarantees that K is contained in some finite subcover of open sets of Y. Now for the other direction, suppose K is compact relative to Y, and that G sub alpha be a collection of open sets of X which covers K. And again, we're using that lemma. We're going to put V sub alpha equal to Y, the intersection of Y and G sub alpha. Well, K is contained in V sub alpha sub 1 and the union of all those all the way to V sub alpha sub n. And since V sub alpha is contained in G sub alpha, well then obviously if K is compact in Y, it implies that K is compact in X. So this is a much shorter proof. And you can see, I mean, if it's compact in Y, it's easier to show it's compact in X. Rather than because K is compact in X, then it's compact in Y. And if this is like the introduction to this notion of compactness, this may be I guess a difficult section to follow. I would definitely suggest or recommend that you go over compactness just on the real line before going over it in metric spaces. And before I do go on, this section is just filled with a bunch of different properties of compactness. So there's a bunch of theorem proofs, theorem proofs, theorem proofs. There's not many definitions other than this open cover and a compact. So with that said, we're going to move to a theorem that says compact subsets of metric spaces are closed. We have this theorem, so we're going to let K be compact subset of a metric space X, and we're going to prove that the complement of K is an open subset of X. Right? We've already proved that a set is closed if and only if its complement is open. So, suppose P is an element of X and P is not in K. Well, if Q is in K, well then let V sub Q and W sub Q be neighborhoods of P and Q respectively. And give me 1 second here. Okay, and their radius is less than half the distance between those two points. Right, this way we can guarantee that the neighborhoods don't overlap. So again, V sub Q is an open neighborhood that is an ugly ball. And Q we have well, since K is compact, there are finitely many points, Q1 to Qn, in K, such that K is contained in those finitely many open sets, which we'll call W. So this is pretty much saying, because K is compact, there's finitely many points there. If we take their neighborhood, the ones over here, their neighborhoods of those points, well then K is just contained in those, in the union of all those neighborhoods. And again, because it is compact, so we're calling that W. Well then, if V is equal to the intersection of all these open sets V, Q1, all the way to V sub Q sub n, then V is a neighborhood of P, which doesn't intersect the union of all those WQ1 to WQn, or W. And Therefore, V is in the complement of K, or is contained in the complement of K. So P is an interior point of the complement of K, thus showing that compact subsets of metric spaces are closed. Another theorem that follows says that closed subsets of compact sets are compact. So it may sound a bit similar to the first theorem, but this one's saying that closed subsets of compact sets are compact. So just have a compact set, I don't know, M, take a closed subset of it, let's call it C, and C is also compact. That's what this theorem is saying. So, to prove this, we're just going to suppose F is contained in K, which is contained in X. I'm going to say that F is closed relative to X, meaning F is closed in X, and K is compact. So, we're going to let V sub alpha be an open cover of F. And if the complement of F is adjoined to this open cover, we obtain another open cover, omega of K, and therefore an open cover of F. Well, if the complement of F is a member of phi, we remove it from phi, and we still retain that open cover of F. Right, so we thus have shown that we have a finite subcollection of V sub alpha that still covers F. Therefore, closed subsets of compact sets are compact. And yet, we have a corollary. If F is closed and K is compact, then their intersection is compact. This theorem shouldn't be too hard to prove. I believe it's also in the book, but you can use previous theorems to kind of make this proof maybe 1 or 2 lines long. Okay, moving on to the next theorem. It says if K sub alpha is a collection of compact subsets of a metric space X, such that the intersection of every finite subcollection of K sub alpha is non-empty, then the intersection of all K sub alpha is non-empty. So this shouldn't be too hard to prove. We're going to fix a member K1 of K sub alpha and put G sub alpha to be the complement of K sub alpha. And we're going to assume that no point of K1 belongs to every K alpha. So the reason we're assuming that no point of K1 belongs to every K sub alpha is because if we just get K sub 1, the intersection of K sub 1, and another K sub alpha, I don't know, let's say 4, their intersection will be empty. Right, so that's why we're assuming that no point of K1 belongs to every K sub alpha. Well, then the sets G sub alpha form an open cover of K sub 1, right? Because G sub alpha is equal to the complement of K sub alpha. So G sub alpha form an open cover of K sub 1. And because K1 is compact, there are finitely many of these G sub alphas that contain K sub 1. Well, then that would mean that K sub 1 intersection with all these other K sub alpha sub 1 all the way to K sub alpha sub n is empty, which contradicts our hypothesis. Right, it contradicts that every finite subcollection of K sub alpha is non-empty. So once we assume that no point of K1 belongs to every K sub alpha, once we assume that, we get a contradiction. Therefore, our theorem holds. And our last corollary, if K sub n is a sequence of non-empty compact sets, such that every Kn is contained in Kn sub n plus 1 for all n, then the intersection of all those sets is not empty. Okay, so like I said, a lot of blue on the screen because this section is really just compact sets and properties of compact sets. Theorem proof, theorem proof, theorem proof. It is a bit long. You might want to take a little break. But we're going to continue going over properties of compact sets. So next we have a theorem that says if E is an infinite subset of a compact set K, then E has a limit point in K. Okay, so we begin this theorem, this proof, where it says if no point of K or limit point of E, then each Q and K would have a neighborhood which contains at most one point of E, namely Q if Q is in E. What does that tell us then? Well, that no finite subcollection of V sub Q can cover E, right? And the same would be true of K, since E is contained in K. But we're assuming already in the theorem that K is a compact set. Therefore, this contradicts the compactness of K and our theorem holds. Next, we have that if I sub n is a sequence of intervals in R1 such that In is contained in In plus 1 for all n, then the intersection of all that is not empty. So I'm going to draw a real line because we are dealing with a real line here to kind of illustrate this, how we're doing this proof. So if In is An, let's do An, Bn. We're going to let E be all the sets in the form A sub n. So let E be the set of all A sub n. Then E is non-empty and bounded above by B1, obviously. Right, because B1 is that first one. So it would kind of look like this. Let's say this is A1, B1, B2, so on and so forth. Well, obviously all the A's are bounded by B1. So it's bounded above. So we're going to let X be the supremum of E. Well, if M and N are positive integers, such that this inequality actually, oh my gosh, I'm so sorry. Let me change this. This is actually backwards. In fact, all these, this is backwards. Wow. I was reading this subset thing like this, but it wasn't making much sense. So yeah, so okay, so let me draw this here. So let's say this one is A sub 1. This one is, B sub 1. There we go. This one would be B sub 2, this one would be A sub 2, this one would be A sub 3, A sub 4, A sub 5, B sub 5, B sub 4, B sub 3. There we go. We're nesting the closed interval. Sorry about that. Anyway, we're going to let x be the supremum of E. And again, E is the set of all a sub n. So supremum E, sup of E is equal to x, which would be somewhere here. If m and n are positive integers, well then a sub n is less than or equal to a sub n plus 1, right? Because as we're increasing from 1, 2, all the way so on and so forth, we're I guess the number is getting bigger, right? So it's greater than or equal to it. And then, well, the b's are next, and these are obviously a sub 5 is less than b sub 5, and a sub 4 is less than b sub 4, and this is true for all indices. So a sub n plus n is less than or equal to b sub n plus n. And here, b sub m is greater than b sub n plus n, because with the b's, as we go down in indices, the real number gets bigger. So b sub 4 is greater than b sub 5, b sub 3 is greater than both of those, b sub 2 is even greater than that, and so on and so forth. So x is definitely less than b sub m, right? Because x is the supremum of all a sub n. Well, since a sub m is less than or equal to x, we see that x is in the interval im. And this is true for all m, 1 to, well, infinity. We keep going. Therefore, this in is not empty. The intersection of all these sets is not empty. Sorry about the confusion there at the beginning. But I'm going to go ahead and erase this picture so I can show this corollary, which is pretty much the same thing. We're letting k be a positive integer if in is a sequence of k cells. So a k cell on the real line just looks like a closed interval. K cell on the plane looks like a square, or a rectangle, I should say. A k cell on the R3 looks like that rectangular prism, so on and so forth. So instead of just the real line, we're generalizing this to k dimensions. And it's the same thing. We're showing that all those, the intersection of all those k cells, those nested ones, the intersection is not empty. And the proof is, pretty much the same, just dealing with the k cells. Again, I omit the proof because, well, we just went over one that's really similar, but you can definitely look it up on the book. But now we're going to move on to our two big theorems of this section. I wouldn't say they're the most important. Maybe the last one is, but I'll mention that when you get there. This next one is just kind of long, not too hard to follow though. Every k cell is compact. That should be a lowercase k. I don't know why it's capitalized. But every k cell is compact. How are we going to prove this? Well, we're going to let I be a k cell consisting of all the points x equal to that list, x sub 1 to x sub k, such that this inequality holds. A sub j is less than or equal to x sub j, less than or equal to b sub j. And this is just how we define the k cells. And I think we defined it last lecture, if I'm remembering correctly. For all 1 to k, I want to let delta equal, you may recognize this. This is like if I were to write this out, sorry. Getting this mixed up. B sub 2 minus A sub 2 squared. A sub K, B sub K. It should be B sub K minus A sub K squared. That's what that is. This is what we're setting delta equal to. Well, then delta is definitely greater than or equal to x minus y, as long as x and y are in I, right? Are in the way in the I in the K cell. And if you're taking a linear algebra course, maybe you can kind of like visualize this. Obviously, mostly in 3 dimensions. But the whole concept of the Euclidean norm may help you visualize this. So I said alpha is greater than or equal to x minus y, the difference between x minus y. Well, to get a contradiction, we're going to suppose that there exists an open cover G sub alpha of I, which contains no finite subcover of I. Meaning I won't be able to be compact, but we're going to get a contradiction. We're going to put C sub j equal to A sub j plus B sub j over 2. What is that going to do? That's going to split. So the intervals A sub j to C sub j and C sub j to B sub j, just split the interval A sub j to B sub j in half. Or not in half. Yeah, right. In half. As it shows here. And it's going to split it constantly, or not for every k. Right, so there's going to be 2 to the k cells, which we're going to call qi, where if we take all the union of those, it forms a whole set I, the whole k cell. So again, every iteration, we're going to split it in half, and then those in half, and those in half. That's why there's 2 to the k cells. Well, at least one of these sets, qi, we're going to call it I1, can be covered by any finite subcollection of G sub alpha. And why not? Well, because we're already assuming that G sub alpha of I contains no finite subcover of I. So there has to be at least one of these sets, we're calling it I sub 1, that can be covered by finite. Otherwise, all of them would be able to be covered by finite subcover. So we're going to next, again, we're assuming that I sub 1 cannot be covered by a finite subcollection of G sub alpha. So we subdivide I sub 1 and continue this process. And we're going to obtain a sequence of I sub n with the following 3 properties. First thing is that we're nesting these, right? I is getting smaller and smaller, but it's contained in the previous one. So like the intervals in the last proof, where they were nested, these i's are getting nested. Also, In is not covered by any finite subcollection of G sub alpha. Again, because of this up here. Because if this weren't true, well then this up here wouldn't be true. And the last property is that if x is in I sub n and y is in I sub n, well then x minus y is less than or equal to 2 to the negative n times delta. That one may not be so easy to see. This is equal to 2 sub n. Which, if you just think about it, because we're subdividing these in 2 every single time, that inequality does hold. Well, by property A, And the theorem from the last slide, saying that the intersection of all K cells is not empty, there's a point x star which lies in every I sub n. For some alpha, we're going to say that x sub x star, that point x star, is contained in G sub alpha, which is this open cover. And since G sub A is open, there exists an R such that the difference between Y and X star is less than R, which implies that Y is also in G sub alpha. Now, if n is so large that 2 to the negative n times delta is less than R, well then C implies that I sub n is in G sub alpha, which will contradict this property here. But how do we know that there is such an n that this is true? If n is so large, well, how do we know that that n exists? Well, because then we would have that 2 to the n less than or equal to delta over R. For all positive integers n. And well, that really can't be true because the real numbers are Archimedean, so this can't hold true for all positive n. That's how we know that this n exists, which then gets us this contradiction over here. Therefore, our theorem follows. And there's tiny little details that you may want to kind of verify. It's always good to do in books when reading. But now we're going to move on to our next theorem, which is the last theorem. At least the last theorem with the proof and the last slide. So, if a set E and R K has one of the following three properties, then it has the other two. Right? So the first property is if E is closed and bounded. Next one is E is compact. Next one is every infinite subset of E has a limit point in E. And this here, that these imply each other, is actually has a name. This is known as a Heim-Borel theorem. If a set is closed and bounded, then E is compact. That's always true in RK, but not always true in every metric space. But the counterexample for that won't be really shown. We won't get into that till way later, maybe like chapter 10 or 11, when we go over Lebesgue measure and when we start defining all the L spaces. But ignore what I just said, and we're going to show that these three properties, that if E has one of these properties, then it has the other two. So first things first. Well, if E is closed and bounded, meaning if A holds, then E is a subset of I. For some K cell I. So E is compact since closed subsets of compact sets are compact, and every K cell, well, is compact. Right? So it's basically saying I is compact. It's a K cell that's compact. E is a closed subset of it. Therefore, E is also compact. So that shows that A implies B. Now to show that B implies C, recall that if E is an infinite subset of compact set K, then E has a limit point in K. And here, how do we know that E is an infinite subset of a compact set K? Oh, because E is a subset of RK and is compact. Right, so E must have a limit points in K, which therefore means that B implies C. So we show that A implies B, B implies C, but now we need to show that A implies, C implies A. This is the one that takes a bit of work. So, if E is not bounded, then E contains points x of n such that the absolute value of x of n is greater than n for all n, right? It's not bounded, so there's unbounded points. Well, then the set S consisting of these points x of n is infinite and has no limit points in RK, right? Because, well, it's diverging, it has no limit points. So therefore it has no limit points in E. Therefore, C implies that E must be bounded. Right, so we already showed here that E is bounded. But what about closed? Okay, well, if E is not closed, then there's a point x naught in RK, which is the limit point of E, but not a point of E. So it's a limit point of E, but not a point of E. Right, and this is because E is not closed. Well, then for n equal to 1, or just keep going on from infinitely, there are points x of n in E such that the distance is less than 1 over n, right, because we're getting a limit point. Well, then S, we're going to let it be the set of all these points x of n. Well, then S is infinite, and S has x naught as a limit point. And before I say here, S is infinite, why is S infinite? Well, because otherwise we would have that x of n minus x naught would have a constant positive value for infinitely many n. Right, so that can't happen, so therefore S is infinite. S has x naught as its limit point, as we're showing here. And we assumed over here. And S has no other limit points in RK. Okay, well then, if y is in RK and y is not equal to x naught, well then this difference, xn minus y, is greater than x naught minus y minus xn minus x naught. And this, we know, is greater than x of naught minus y minus 1 over n, since this here is less than 1 over n. Sorry, yeah. And we know that is greater than or equal to half the distance between x of naught and y. For all but finitely many n. So this shows that y is not a limit point of S, thus showing that S has no limit point in E, hence E must be closed if C is to hold. So again, if C holds, then E is closed. And we previously showed that it was also bounded. Therefore, C implies A, and this proof is done. The last theorem before ending this section, you can try to prove this. It may be in the book, it probably is. But using these past theorems that we've been using in this section, you should be able to prove this pretty easily, not knowing these properties of compact sets now. And that theorem is known as the Weierstrass theorem. It says every bounded infinite subset of Rk has a limit point in Rk. And that should conclude the lecture for today for compact sets. And then we'll be looking at perfect sets and connected sets next.